Check it out now, y'all.
nanoHUB-U, online instruction.
All right, welcome back. We spent a couple of lectures discussing digital circuits. To wrap up the course, what I'd like to do is to spend this lecture discussing analog circuits. We're going to go very quickly, just discuss a few high points, try to understand what are the key device metrics that analog designers are interested in, so that as device technologists we have some appreciation for what we have to build. We're going to start with our familiar CMOS inverter. So we're familiar now with its transfer characteristic. We've been discussing this for a couple of lectures. One of the points we made is that in the transition between when the device switches from low to high input, high to low output, we have a steep transition. And the slope of that is something that we call the gain. So we're going to use the same circuit, but we're going to use it in a little bit different vein now, actually quite a different vein. Instead of switching the input from 0 to VDD, we're going to bias the input halfway in between, which will bias the output halfway in between. That's a DC bias, and we'll call that Q, the quiescent point. And we're going to keep the DC voltages there. Now what we can do is we can add to the input a small AC voltage that makes that input voltage get a little bit bigger and a little bit smaller. And as it gets a little bit bigger, we'll have a little bit lower output voltage. And as it gets a little bit smaller, we'll have a little bit bigger output voltage because the gain is negative in this circuit. And you can see that what happens is that because the magnitude of the slope is greater than 1, we're going to have an amplification of the output signal. It'll be bigger than the input signal. So we have small signal amplification. It's negative in this particular circuit, but its magnitude is bigger than 1, so we can amplify signals. Okay, so there are lots of applications for analog and RF. I've listed several of them here, so there are many important applications. You might wonder why use CMOS for this, since we discussed 3.5 transistors and we learned that they're very good high-frequency devices. Well, one of the reasons is that many circuits are both analog and digital. So if you're building a digital system and you need a little bit of analog, you'd like to do it with the CMOS technology that you're doing the digital system with. It's the dominant technology, so it's widely available at low cost. And what's happened recently, in not too many years past, is that device scaling has made transistors smaller and smaller and smaller, and that's made CMOS transistors faster and faster so that they can do useful things at very high frequencies. So that's made CMOS RF an interesting topic. We discussed in the last 2 lectures the key figures of merit for digital circuits. The point of this lecture is to try to understand what are the key device metrics for analog electronics. So we're going to be talking about small signals. So we have a DC signal and an AC signal. There's no DC gate current except for leakage current, but there is a small signal AC current, and we can represent that as just the capacitance between the gate and the source. So that's the small signal AC current just flows in response to the small signal AC voltage on the gate. Now, there is a DC current that flows in the drain. We've talked about DC IV characteristics. We understand all of that. There is an AC current that flows too. And the AC current is transconductance times the AC input voltage. And transconductance is easy to understand. It's just the ratio of the output current to the input voltage, small signal both. These are like little delta IDs and delta VGs, so that's like a derivative. If we take the derivative of the DC IV characteristic, then what we're doing is assuming that the device is inherently fast enough that it can keep up with this rapidly varying input voltage. That's a quasi-static assumption that typically works very well unless we go to very high frequencies. So we can easily compute what that transconductance is. So let's take a look at that transconductance, because that is the key figure of merit for these devices, for the analog device. It's just a derivative of the output current with respect to the gate to source voltage let's compare it to a bipolar transistor. The transconductance of a bipolar transistor would be the derivative of the collector current with respect to the base emitter voltage, its input voltage. So we know what the drain current is for a MOSFET. We know what the collector current is for a bipolar. We can do the derivatives. We'll get a simple expression for the transconductance of the MOSFET, width times C inversion times average velocity at the virtual source. We'll get an even simpler expression for the transconductance of a MOSFET. It's just the DC collector current divided by KT over Q. Okay? So you can see that a key figure of merit is going to be if we bias the device at some DC current, which will dissipate some power, how much transconductance can we get out? Transconductance is what makes this useful as an amplifier. So a key figure of merit is transconductance per drain current. And since the drain current goes as VG minus VT, for a MOSFET, it'll be proportional to 1 over VG minus VT. In a bipolar device, same thing, just divide the two, it'll be equal to 1 over KT over Q. So here's where the big difference comes. For a MOSFET, we might have a power supply of a volt or so and a small VT. This figure of merit will be about 1 inverse volts. For a bipolar, KT over Q is 0.026. The figure of merit is about 40 inverse volts. So inherently, a bipolar transistor is 40 times better in terms of transconductance. It really is a much better analog device inherently than a MOSFET. And that happens because the base emitter voltage is applied directly by base contacts and emitter contacts, whereas in a MOSFET, we're modulating the source to channel barrier indirectly through this gate. So the device ends up having a smaller transconductance. So MOSFETs can be useful for analog, but they're inherently, in principle, they're just not as good as a bipolar transistor. If we plot the transconductance versus VGS, below threshold, there isn't much transconductance. Above threshold, it's just width times capacitance times velocity. And what's happened is that as devices have gotten shorter and shorter, the velocities have gotten bigger and bigger, capacitances have gotten bigger too, so the transconductances have gotten large enough that we can do useful things with them. Now, just as an aside, let's look in subthreshold just to see what happens. Below threshold, our definitions of transconductance don't change. But the subthreshold current for a MOSFET goes exponentially with gate voltage, not linearly like it does above threshold. The nice thing about a bipolar transistor is the IV characteristic is always exponential, below and above threshold. There really is no threshold. So the transconductance, then, we can do a simple derivation, just do that derivative. It's very similar to what it was for a bipolar. There is just this voltage divider ratio M. That's the ratio of the oxide capacitance to the semiconductor capacitance, and which can be a little bit bigger than 1. So our figure of merit then is just 1 over M KT over Q, and for the bipolar it's 1 over KT over Q. Put in numbers, and you can see from this figure of merit, in the subthreshold regime, these devices are very, very similar. They provide very similar amounts of gain, very similar figures of merit. The difficulty is the transconductance goes as drain current, as the DC bias drain current. In the subthreshold regime, that's very small. So the figure of merit is good, but the actual transconductance is very small because the actual current is very small. But it's nice to understand that those two devices really are almost the same device in subthreshold. Okay, so if we look at small signal current gain, if I build an amplifier this way, so I hook an N-channel device to a resistor, I'll have some small signal current that will flow through it. If I'm taking my output down here, then my output voltage is on the bottom. I'll ignore the DC voltage, so that's just like AC ground. My output voltage is minus transconductance times input voltage. That gives me the small signal current times the value of that resistance. So the result is that we get a very simple expression for the gain of this little small signal amplifier, it's minus transconductance times the value of the resistor in the drain circuit. Now in a real device, the transistor will have some output slope, which means it has some output resistance. That means that my equivalent circuit should show an output resistance between the drain and the source, and that output resistance will affect the performance of the circuit. And what we'll find is that this output resistance is in parallel with the actual resistor in the drain. So my gain is lowered a little bit because it's the drain resistor in parallel with the output resistance. Better the output resistance, the higher my gain is. Now, why is this important? Well, analog circuit designers are very, very clever. They can do circuit tricks with current mirrors that basically effectively make the value of that drain resistor to be very, very high. You know, in principle, you could ask, what if this drain resistor goes to infinity? Then the maximum gain that you could ever get would be minus G sub M of the transistor times R out of the transistor. So this is a figure of merit for the device itself. It's called the self-gain. The higher the self-gain, the better. If you've got a good transconductance and if your output resistance is not too low, you'll get a decent self-gain. So just to calibrate you, here's some 65 nanometer digital CMOS data published a few years ago. We can just read numbers off. The change in drain current with respect to gate voltage tells us that the transconductance for this particular device is about 1 millisiemens per micrometer of width. The output resistance is just 1 over the slope of this. It's about 7 kilo ohm micrometers. So we can compute the self-gain. And the self-gain is, you know, not fantastic, but it's on the order of 10. You can do useful analog electronics with a self-gain that's that high. Now, one of the challenges that scaling forces us to do is that the smaller you make the transistor, the lower the output resistance is, because we have all of these short channel effects and dibble that cause the current to increase in the saturated regime. So what you find is that as the devices get smaller and smaller and better for digital, they get worse and worse for analog. So many times you'll see analog circuit designers not using the smallest transistors on the technology, but using longer channel lengths to get higher output resistance and better self-gain. Okay, so we've talked about a couple of figure of merit. Let's talk about high frequency performance, because that's an important figure of merit. So here's my equivalent circuit again. I've inserted a resistor in the gate. Here's my gate to source capacitance. I might have some overlap capacitance between the gate electrode and the drain. I might have some output resistance. And what we want to do is to analyze the performance of this circuit when we squirt in a small signal current at some frequency omega, and we measure the output current at the same frequency. And we'll do that as a function of frequency. Okay. So you can see this is the output current. If I look at this output current, it's primarily, if the output resistance is high enough, it's primarily the current through this controlled current source. I can ignore the one through this small gate to drain overlap capacitance. So that's a good assumption in practice. My input current is not affected by this series resistance of the gate. It just comes into the heart of the device. So I can write my input voltage as input current times the admittance at this point, which is a parallel combination between the gate to source capacitance and the gate to drain capacitance. So I have a simple expression for the input voltage. I can put those two together and I get the output current in terms of the input current, G sub M over J omega C total. And the result is that if I plot the ratio of those two, I would call those the small signal current gain. No, this is what we talk about in a bipolar transistor under DC conditions, but in a MOSFET we have gate current flowing under AC conditions, so we can talk about the current gain. And the overall current gain ends up being a simple relation that's very intuitive. It increases as the transconductance increases, and it drops as the capacitance increases. Capacitors slow it down, Transconductance improves it. So if we plot this gain versus frequency, we'll see that it drops linearly with frequency. Or if I plot it on a log plot, it drops at minus 20 dB per decade of frequency. And if you extrapolate to the point where the current gain drops to 1, now we've pushed the device as far as we can. If the gain is less than 1, it's not very useful as an amplifier. So that frequency, we call omega sub t, is a key figure of merit because it tells us the highest frequency that the device is useful at. If I convert that into ft, it's G sub m over 2 pi c total. So this is a very nice, simple way to estimate the maximum frequency that a device will operate at. Take any new device that you've just invented, if you can estimate its transconductance, if you can estimate its total capacitance, then you have a simple estimate for its gain bandwidth product or the highest frequency that it will operate at. Okay, so, if we look at this gain bandwidth product in a little bit of detail, you can see that it's G sub m over C total. We know what G sub m is. C total is the capacitance in farads, so it's the oxide capacitance times width times length. And if you go all the way through this, you can see that the maximum frequency of operation is basically 1 over the transit time, 1 over the time that it takes an electron to go from source to the drain. Not exactly, but it's close to that. And that's a nice physical and intuitive result. So the other thing that's happened with device scaling is that as channel lengths have gotten shorter and shorter, the transit time has gotten shorter and shorter, and the maximum frequencies of performance have increased to the point where these devices are useful for analog and RF applications. Now, one of the things I'll point out is that this isn't the only high frequency figure of merit. We analyzed a particular circuit and analyzed the current gain for that circuit, and that particular circuit is insensitive to a lot of things that occur in realistic circuits. Another figure of merit that you will frequently see is the maximum frequency of oscillation, or the unity power gain. This is another critical frequency for circuit performance. It depends also on some other parameters. It depends on that FT, but it depends on some things that FT didn't depend on. So this is another figure of merit that circuit designers pay a lot of attention to. So, in summary, our key figures of merit for analog transistors are transconductance, easy and simple to understand, self-gain, which is also another concept that's easy to understand, and then these two critical frequencies, the unity gain bandwidth product, FT, and the unity power gain frequency, fMAX. So there are other key performance considerations that analog designers worry about too. They're very important. We don't have time to discuss them here, so I'll just mention that if you're dealing with analog electronics, you should learn a little bit about those other figures of merit. Okay, let's take a quick look at some analog results. 45 nanometer CMOS, published a few years ago at IEDM, and if you take a look at these results, you can see these are plots of the gain versus frequency, the two key figures of merit here. This one is FT, and you can see hundreds of gigahertz. That's about half of what we had for high performance HEMPs or HBTs, but they're still very high frequencies that are useful for very many operations. This is some more data, which is just showing over time, as channel lengths have gotten shorter and shorter, how these peak FTs have gotten bigger and bigger until they're now in the hundreds of gigahertz regime, where they're very useful for many RF type of applications. This is the measured self-gain for two different transistor designs, and you can see it's on the order of 6 to 10, just about what we estimated earlier. Not big, but big enough for many applications. Okay, so that's been a very quick look at some key figures of merit for analog. Just want to summarize them here. If you're dealing with analog electronics, you want to understand the small signal model. We dealt with just a very simple basic one, but there are some other factors that come in and can become very important. The key parameter in that model is transconductance, which is a nice, easy to understand quantity. Self-gain is also a key figure of merit. It depends on the slope of the output characteristic and sometimes forces designers not to use the shortest channel length. The gain bandwidth product, F sub T, and the unity power gain, fMAX, these are two very important figures of merit that tell us how high in frequency can we use these devices in circuits. And then there are other considerations that we haven't had time to discuss in detail. But as that example shows, you're seeing more and more applications of silicon RF to various applications using conventional CMOS, not only for digital but also for analog applications. But for the most demanding high-frequency applications, designers will still rely on 3.5 transistors, either HEMTs or HBTs, which can offer frequencies of operation that are factors of 2 or so higher than you can get from very small silicon devices. Okay, so that wraps up our discussion of circuits, both digital and analog. It also wraps up the course. So I hope you've enjoyed being with me on this course and that you've learned something about nanoscale transistors. And although we've gone quickly and have only been able to discuss some essential concepts, I hope we've set the stage that you can pursue those topics that you need to and that interest you on your own using this course as a starting point. So thank you for sticking with me. Goodbye.